All right, everyone, welcome back to chemistry. So today what we're looking through is we are doing the iodine clock reaction and kind of examining some factors that affect the rate of a reaction. So this is what we've been going over in class. If you forget, there are 5 different factors that we've looked at that either can speed up or slow down a reaction. We've looked at how changing concentration can affect the rate or how quickly a reaction happens, changing temperature. Let's see what else we got. The addition of a catalyst. Let's see, for one of our demonstrations, we looked at surface area, how if I grind something up into a powder, because it has more surface area, the reaction happens much quicker than if, well, it was in chunks as opposed to a powder, and catalysts. So remember, for rate of reactions, reactions happen when molecules or particles, depending on what we're talking about, when they collide together, if they have sufficient activation energy, so if they hit hard enough, typically if they're at a high enough temperature, then they can react if they have proper orientation also. So when these molecules bump into each other and collide, which we refer to as like collision theory, when they collide, they have to be like facing the right direction to hit to be able to break the bonds of the reactants and then come back together and form new bonds. All right, so today we're looking at a chemical reaction, and we are looking at how 2 of those factors affect its rate or its speed. We're looking at how concentration of one of the reactants and change in temperature affect it. So let me show you the reaction for a second. This is called the iodine clock reaction. All right, let's see how Microsoft Teams lets me switch screens. How long will it take? Be patient with me for a second. By the way, just a reminder, you've got that, while I'm waiting for this to load up, you've got that exam coming up on Monday. I posted the study guide answers in the chat, not the worked out solutions, just the answer parts. But yeah, study guide's there. Study guide will be due after you take the exam. For those of you guys who are virtual all the time, that exam will be on CK12. For anybody else who's watching this because they just missed the day that we did the lab, you're still good, but you'll be taking it in class. All right, here we go. Oh, Microsoft Teams. All right, so we've got a pretty complicated reaction here. I mean, it looks pretty easy when you'll actually see me do it. We end up mixing something called potassium iodate with something I'm just going to refer to as solution B, which is a mixture of some other stuff together. And the reaction, all of these different reactions happen at the same time, and we go from aqueous, colorless, or clear solutions all of a sudden to this dark blue colored complex that tells us that the reaction's over. So like a lot of chemistry, kind of looks like a pretty simple reaction, but a whole bunch of stuff is happening at once. All right, let's take a look, because it's a pretty fun reaction. I certainly like it. All right, we'll switch screens, collect some data, and then you'll be able to complete this little guy. All right, there we go. Okay, we're going to do this reaction in this cup. And so for our first trial, I'm going to have 50% of the potassium iodate. Let's go with 20 milliliters. %50 of potassium iodate. I'll put it in this little cup right here. Let's make sure I get that right under there. We go. And then I'm going to do 50% of okay, let's see. Just a second. Let me pause this video and go rinse this thing out, because I forgot that how careful I have to be about contamination. If I let these 2 things touch, it's going to screw up the whole reaction. Because my kids use so much of my substances, I'm worried I'm going to run out. So give me 10 seconds. All right, I'm back. I don't know how your kids are, but my kids, when I bring home chemicals, they just want to play with them. And they do, and then they use them all up, even though Dad said, be careful. All right, so this is solution B. It's kind of like a cloudy little it's kind of like a cloudy little substance. It's got some potato starch in it, which is essentially like cornstarch that we use for cooking. But because it keeps settling to the bottom, I've got to really swirl this guy together to get it going. So I'm going to measure out 20 milliliters of this. I'm going to be a lot more careful that I don't use the same graduated cylinder for each substance, so I want you to see the reaction. I don't want it to happen in here. All right, so I'm going to mix this together. I'm going to get my phone ready. And we're going to time how long this reaction takes. So this is 50% of each, equal concentrations. On your mark, get set, go. And I'll start to, oh, stop. Well, okay, that one went quick. So we're going to say 3.95 seconds. And yes, I know you're sitting there thinking, this guy needs to work on his reaction time. It's hard to be old. All right, let's see if I can do a slightly better job this time. Okay, so this time I'm going to change the concentration. And let's see if it affects how long this reaction takes. So now I'm still going to use the same 20 milliliters of solution B that I did before. Swirl this little guy up for a second. All right, I'll leave that here, ready and waiting. But now, in a new cup, I'm going to mix together. Before I had 20 milliliters of KiO3. This time I'm just going to do 10. And the other 10, I'm just going to do with regular old water. In the lab, we would have distilled water. I don't have any of that, but I found it doesn't matter too much, especially when I forgot it at school. All right. So now I've reduced the concentration of KiO3. So what happens when you reduce the concentration for the rate of a reaction? Well, let's find out. All right, so I'll try to keep everything the same before. I'll pour this, I'll hit start, and I'll start to swirl, and let's see how close it is to that. Deep breath. Ooh, 5.18. Still pretty close, huh? Just took a little bit longer. 5.18 seconds. And you can probably guess if I reduce that concentration of KiO3 even more, you'd see it even take longer. Kind of regretting I didn't do it this time, but again, darn kids used up all my KiO3. You know how they are. All right, so that's a relationship between concentration and time. As you'll see for the data we'll collect in the graph, the lower the concentration, the longer a reaction like this will take. We got to the point in the lab where some people, once you got down to like less than 10% of one of the reactants, sometimes it took up to like over a minute for this reaction to happen. All right, so we've looked at concentration versus time. Now let's try something different. Let's look at temperature versus time. So for all of these trials, both of them, I'm going to keep the concentration of each substance the exact same. So it's just going to be 50-50 mix. So that would be some controls in my reaction. The independent variable, in this case, is going to be temperature, IV for independent variable, the thing that I am changing. And then the thing that I'm recording as my data would be the dependent variable. That's going to be time, measured in seconds. All right, so let's see how this goes. All right, I have a cup. I'm going to go ahead and put, let's see, 20 milliliters of solution B in there. Go ahead and measure that out. All right, 20 milliliters of solution B. And so for this first one, I've got some KiO3 that's been just soaking in a glass of ice water for a while. So it should be colder. I'll go ahead and wait till the reaction's done, and then I'll measure the temperature of it. All right. Let's see what you can do, little buddy. All right. Your mark, get set, react. Dude. Okay. 2.69 seconds. And our temperature for that guy was 13.5 degrees Celsius. So that was an unexpected result. All right, let's see if we can do the same thing when it's even hotter. All right. So, gonna measure out my 20 milliliters of solution B. Got my thermometer ready. This thing's reset. All right. Now, over here in this hot water thing, I've got a little more KiO3. We'll mix that together. Let's see if it happens any faster. All right. On your mark, get set. Oh. All right. That one happened really quick. What do we have for our temperature there? I'll stir it around for a second, see if I can get this to record. We don't need to get the temperature perfect, but it looks like it slowed down. Oh, okay, it stopped at 29.0 degrees Celsius. So at a temperature of 29.0 degrees Celsius, it took us 1.51 seconds. Took much faster. Got to be honest, I kind of regret the way that I did this thing. I think as we'll see, I used quite a bit of stuff, and it would have been better if I had a bigger difference in temperature. In class, I had it in an ice water bath for quite a while, and this temperature was down into the single digits, and the high temperature was about 60 or 70 degrees Celsius, so it was much hotter, and there was a huge difference between the two. So you can see the two. I'm going to go ahead and post in the assignment section the data from one of the students in your class, and you'll see that it's a pretty clear connection. Although it is here, you should see that when the temperature goes down, those molecules are moving a little slower, and so the reaction takes longer than when they're moving faster. And why does it take longer when they're moving slower at lower temperatures? Well, as those molecules and particles collide with each other, they have less overall kinetic energy. So fewer of those collisions between molecules have enough activation energy to get the reaction going. All right. So let's see. Let's go ahead. We've gathered the data. I'm going to go ahead and show you a data table from one of the students in your class. So let's see if it's going to let me share screens again. This time it happened a little faster. All right, so I just stole the data. In this case, I think it was somebody from 7th hour. So here, they were decreasing the concentration of KiO3. They weren't using percentages like I was, but it's the same type of thing. And they kept the amount of solution B constant. So as the amount of KiO3 went down, the reaction took longer and longer. Over here on this side, when they looked at temperature versus the rate of reaction, we had some low temperatures and some high temperatures. At the lowest temperature, it took closer to 20 seconds. And at the high temperature, it took quite a bit less time, 4.6 seconds. So all you had to do for this lab is you had to make a decent graph about it. So at the bottom of this thing, and again, I'm going to post this document right here in the assignment section, but here you're going to need to make a graph. On the back of this document is some graph paper, or you can just draw your own graph, and it doesn't have to be on graph paper. Include that, and then just take a picture of it and upload it when you upload your assignment. All right, let me talk about what you need to do for this graph, and then I'll let you get out of here. All right, so you've got two different graphs. Let's see. Let's go ahead and go. Sorry, better switch screens. There we go. All right. So here over on the y-axis, I'll just pick the reaction. Let's see. We'll do the one between temperature versus time. All right, so first off, make some decent sized graphs. You don't need real small graphs or anything. Make sure you label your graph, and then you give it a title, and then label the axes. Almost always our dependent variable, the thing we measure, is going to be time, and that's going to be on the x-axis. So I'm going to write time down here. Make sure you include the units. It's time measured in seconds. Over here, I'm going to use temperature. And my units for temperature are going to be degrees Celsius. All right, so let's think about the range of temperatures that I need. Well, let's see. I will go ahead and what you want to do is you want to look at what the lowest temperature is. And so let's say our temperature range, as we look at our data, when I don't remember what it was on that other screen, but let's pretend it went between 50 and 70 degrees Celsius. That's the lowest value and the highest value. Now, when you're making a graph, you don't have to start at 0. And when you draw a line, it doesn't have to go through 0, any of that stuff. So if my lowest value is 15, maybe I'm going to start down here at 10. I need to make sure that this graph goes up until a little bit above my highest value. So if my highest temperature was 70, maybe I make sure my graph goes to 75. And then, well, I just kind of pick units that go in between there. So let's say 15, 20, 30. Now you're going to have little boxes. You have actual graph paper, so yours is going to look a heck of a lot better than this thing I'm doing. 50 as I try to cram stuff in here. 60. Well, that would be 70. We'll call this 75. I don't think this graph's going to win any awards, but hopefully you get an idea. You don't want a bunch of wasted space at the bottom of the graph or at the top of the graph. So that's why I'm not going clear down to 0 and I'm not going clear up to 100. We want the line that we make for this graph to take up a lot of space so that, well, if this was a real chemistry experiment, we were using this data for stuff, we could go through and we could make a lot of predictions based on the slope of that line. Okay, so if that was my temperature, now I've got to look at my range of times. So what were my times in here? Let's see, I think if I remember on that last one, let's say my lowest time was 3 seconds and it went up to 20 seconds as my highest one. Well, that's not too crazy. So maybe I take a look at that and I'm going to I could start that at 0 since my lowest value is 3. So maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20. All right. So you get a range here on my x-axis that's going to encompass all of my data points, but not have a bunch of wasted space on either side. And now you've got to plot your data. So you'll be making 2 different graphs, one which is temperature versus time, one which is concentration versus time. And so let's say I plot my data points and I get a point here, 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 and here. Maybe those are my 4 data points. What do I do with that? Okay, so you plot your data point in, and what we're looking for now is we're looking to make something called a line of best fit. Kind of like a line in here that's going to average all those points together. So these little points that I picked aren't great, but normally we would plug this into a computer and plug in line of best fit, and it would make an average line that shows us what these points are. And that would be useful to us because let's say I wanted to design a reaction, or I wanted to pick a temperature that took exactly 10 seconds. Well, then I could say, 10 seconds, I could go up here, I could track it over, and I could know exactly what temperature I need. I could learn stuff about this experiment. I could predict things from this experiment based on these data points that I made in that line of best fit, even for temperatures that I didn't even test. All right. So we aren't going to plug this into any graphing software. So what I had students do is use a ruler or something else. You're not playing connect the dots. You're trying to just pick a line that's going to be kind of an average of those points. Maybe that's my line of best fit. And again, your data is not going to be perfect. So it's not going to go, it's probably not going to go straight through any of the points. But hopefully the total amount of space up on this side is pretty close to the total amount of space on that side as we average in these distance between our points. I'm not looking for anything too crazy. If I was, we would do it in Logger Pro or Excel or Microsoft Word or somewhere else where we can make a nice graph. Okay, so that's all I'll be looking for you. 2 nice graphs, temperature versus time, concentration versus time. Make sure you give each graph a title. You label your X and Y axes, even with units. You make sure the range covers the lowest and highest values. Other than that, I'll see you on Monday. This assignment here is not going to be due for you, these two graphs, until Wednesday. So I'm a little late getting this posted for you, and you have an exam Monday you should be focused on anyway. So when that exam's over, you can use Tuesday in class, and then Wednesday, by the end of the day, this little guy will need to be in. All right, thank you for joining me. If you have any questions, shoot me an email. Otherwise, have a good one, guys. Catch you later.